Okay, so in the previous one, we have talked about the congruence on integers in this chapter. So we said that for an integer m, for a positive integer m, a comma b are and for a comma b as an integers, if m divides b minus a, we write that a is congruent to b mod m or modulo m. So this is how we define the congruence on integers. And there are some propositions that every integer n is congruent to exactly one of the numbers modulo m. And then we have did some of the examples. Then this one was the proposition. So congruence follow the identity or the closure law, follows the like a congruent to congruent b, it's symmetric, and then this is reflexive, symmetric, and then the other one. I don't remember, sorry, the name. Okay. Now we will talk about that some arithmetic congruences. So arithmetic. Okay. Right. So congruence is a notation that conveniently records various divisibility properties of integers. This notation comes into its own when we do arithmetic with congruences, as we show is possible in the next two results. The first shows that congruence modulo m can be added and multiplied. Okay, so let's give the proposition. (13.3). This proposition says that suppose A is congruent to B modulo M and C is congruent to D modulo M, then A plus C is congruent to B plus D modulo M, and A multiply C is congruent to B multiply D modulo M. Okay, and we can prove this. So we are given that M divides B minus A and M divides D minus C. Now say that B minus A is some K prime M, K times M, and D minus C is some L times M, where K and L are some integers. Then B plus D minus A plus C is K plus L times M, and hence A plus C is B plus congruent B plus D modulo M by this above thing. Okay. And BD minus AC is A plus KM into C plus LM minus AC. Okay. And then this can be written as M into AL plus CK plus KLM. Okay. Which implies that, and this implies that AC is congruent to BD modulo M. And this is the, have we completed the proof? Okay. The other proposition is (13.4) is that this says that if A is congruent to B mod M and N is a positive integer, then A power N is congruent to B power N modulo M. Okay. We can also prove this. So we prove this by contradiction. Let P of N be the statement of the proposition. Sorry, prove this by induction. Yes. P of N be the statement of the proposition. Okay. Then P of 1 is obviously true from the statement. Okay. Now, suppose P of N is true. So A power N is congruent to B power N modulo M. Now is A is congruent to B mod M. We can use proposition 13.3 to multiply these congruences and get A power N plus 1 is congruent to B power N plus 1 mod M. which is P of n plus 1. Hence, and this is true by the proposition 13.3. So hence, P of n is true for all n by induction. Perfect. And this proves the proposition. Now, these results give us some powerful methods for using congruences, as we shall now attempt to demonstrate the few examples. So let's do some examples. So example 13.2. So the question is, find the remainder R between 0 and 6 that we get when we divide 6 power 82 by 7. Okay, let's try to find that. Solution. So we start with the congruence. That 6 is congruent to minus 1 mod 7. Okay, now by proposition 13.4, we can raise this to the power 82 to get that 6 power 82 is congruent to minus 1 power 82 mod 7. Hence, 6 power 82 congruent is going to be 1 mod 7. This means let's write it on the next line. This means that 7 divides 6 power 82 minus 1, and hence 6 power 82 is equal to 7q plus 1 for some q in z, and so the remainder is 1. So you can see we can find out the remainders. Okay. Now let's try to do another one. (13.3). Which says that find the remainder between 0 and 12 that we get when we divide 6 power 82 by 13. Okay. Solution. This is not easy as the previous example. So we employ a general method which involved successive squaring of the congruence. So we use a general method which involves successive squaring okay right of the congruence six mod congruent to 6 mod 13. Now squaring once we get we get 6 square mod 36 mod 13. Now since 36 is congruent to minus 3 mod 13, then proposition 13.23 gives 6 square is congruent to 3 minus 3 mod 13. Now successive squaring like this yields that we will have 6 square is congruent to minus 3 mod 13. 6 power 4 is congruent to 9 mod 13. 6 power 8 is congruent to again 3 mod 13. And if you go on further, 6 power 18, 16 is congruent to 9 mod 13. 6 power 32 is congruent to 3 mod 13. And then 6 power 64. 6 power 64 is congruent to 9 mod 13. And if you go further, and now 6 power 82 is equals to 6 power 64, 6 power 16, and 6 square. If you just add these two, okay? Now multiply the above congruences for applying the above congruences for 6 power 64, 6 power 16, and 6 power 2, we get 6 power 82 is congruent to 9 times 9 times minus 3 mod 13. Now, we know that 9 times minus 3 is minus 27, and that is mod minus 1, congruent to minus 1 mod 13, because 13 times 2 is 26, and that will be remainder will be minus 1. So 6 power 82 is congruent to minus 9, which is congruent to 4 mod 13. Hence, the required remainder is, hence, the required remainder is 4. Now, why minus 9 is congruent to 4? Because if you subtract minus 9 from 13, you will get 4. So that is how we say the remainder works. Okay. Now, that is the way to do these things. Okay. Now so the method given in this example is called the method of successive squares. So you can write it, the golden one. So the method given in this example is called the method of successive squares, and always work to yield the congruence of a larger power given some effort. Okay. Now, to work out the congruence modulo m of a power x power k for some integer x, express k is sum of the powers of 2. You might have met this before as saying writing k in base 2 or some such phrases. So say k could be written as this. So let's define this strategy. So we are saying to work out the congruence modulo m of a power x power k of some integer x, express k is a sum of powers of 2, say k can be written as 2 power a1 plus 2 power ar, then successive square to work out the congruence modulo m of the powers. Now then successively square to work out the congruence modulo m of the powers 2 power a1 up to 2 power ar and multiply the ends these together to obtain the answer. To obtain the answer. Sometimes this effort can be reduced with some clever trickery, as an example 13.2. Okay. Few more examples. So we want to understand best. Example 13.4. And this says, show that no integer square is congruent to 2 modulo 3. In other words, the sequence 2, 5, 8, 11, 14, 13, 17 contains no squares. You can say, in other words, the sequence, which one? The sequence 2, 5, 8, 11, 14 contains no squares. Okay. Solution. So consider an integer square n square, where n is an integer, and by proposition 13.1, n is congruent to 0, 1, or 2 modulo 3. Okay. Now, if n is congruent to 0 mod 3, then by proposition 13.4, we can say that n square is congruent to 0 mod 3. Similarly, if n is congruent to 1 mod 3, then n square is congruent to 1 mod 3, and if n is congruent to 2 mod 3, then n square is congruent to 4 mod 3, and hence using 13.23, we get n square is 1 mod 3. Because if you divide 4 by 3, you will get the remainder 1. Okay. This shows that integer square are congruent to 0 or 1 modulo 3. Okay. Perfect. Right. Then move further and talk about some other example. Then that would be the example 13.5. Says that show that every odd integer is congruent to 1 modulo 4. Okay. The answer would be, this is similar to the previous example. So let n be an odd integer okay, then n is congruent to 1 or 3 modulo 4. So n square is congruent to 1 or 9 modulo 4. Hence, to 1 modulo 4, because 9 can be reduced to 1 modulo 4. Okay. Now, unlike adding and multiplication, we can't always divide congruence modulo m. For example, so let's write the fact. We cannot always divide congruences modulo m. For example, ten is congruent to 6 mod 4, but we cannot divide this by 2 to deduce that 5 is congruent to 3 mod 4, which is wrong. However, the next result shows that there are some circumstances in which we can divide congruences. So let's talk about those circumstances by providing this result. Proposition 13.5. Number 1 says, let A and M be co-prime integers. Co-prime integers if x comma y are integers and are such that xa is congruent to ya mod m, then x is congruent to y mod m. Now this is very interesting because you can see that A and M are co-prime because that means they don't share any common divisors. So if that is the case, then we can divide it by A. Okay. Part 2, number 2 is let P be a prime and let A be an integer that is not divisible by P. Now, if x comma y are integers, such that xa is congruent to ya mod p, then x is congruent to y mod p. So if p be a prime and a be an integer that is not divisible by p, then they are co-prime to each other, and x comma y. So then xa is congruent to ya mod p. Then we can write x congruent to y mod p. Perfect. It is very good. And we can prove this. So number 1, assume that xa is congruent to ya mod m. Then m divides xa minus ya, which is equals to x minus y into a. Now, since A and M are co-prime, proposition 10.5, A implies that M divides x minus y. Or in other words, x is congruent to y mod p. Okay. Number 2. So this is immediate from part 1. Since A is not divisible by P, by A prime P, then A and B are co-prime. Then A and B are co-prime. And this proves that proposition. Thank you so much. Do like and subscribe. Thank you.